Welcome to Ready to Derive. By this point in our study of calculus, we know that the definite integral is our magical tool for finding the area under a curve over a specified interval. When we say under a curve, we really mean between the curve and the x-axis. In this video, we learn to adapt our approach to find the area between two curves. We treat two cases, integrating with respect to x, which we are most accustomed to, but also integrating with respect to y, which is sometimes the more efficient approach for finding the area of a region. So let's dive right in. So for our first practice problem, we'll find the area of a region that we are kind of used to finding the areas of. So here's a region that's enclosed by y equals e to the x-axis, the y-axis, and the line x equals 2. And we know that that region between a function and the x-axis, to find that area, it is literally given by the definite integral from 0 to 2, from the lower bound to the upper bound, of the function e to the x dx. Let's think for a moment like why that is when we're finding the area under curve. E to the x, any typical e to the x is literally just the height of this line segment, right? That's e to the x. And as you move that along, e to the x changes in height depending on what the value of x is. And if we add all those vertical line segments, well, before too long, I'm not going to draw them all, but you can imagine shading in the whole region. So think of the integral, remember, is like the summation of all the y vertical line segments from 0 to 2 under this function. So, and we know by the fundamental theorem of calculus that we have to just find the antiderivative of e to the x, which is e to the x, and then we get to plug in the upper bound, e squared, minus plug in the lower bound, e to the 0, and we get out that our answer is e squared minus 1. So that's the area of the orange region at right. So we're going to modify this slightly now. And what if we suddenly sort of introduce this scenario? So instead of going from e to the x all the way down to the x-axis, we're going to kind of take out a chunk. We're going to take out this area here. All right, so we could kind of predict, I mean, I'm looking at this, and this is a triangle, a half base times height, half 2 times 2 should just be 2 square units. And we know that this area up here is e squared minus 1 in total, the total area. So I'm predicting that we would just take e squared minus 1 and subtract out that 2, predicting that e squared minus 3 will be the answer. Let's see how it goes. So what you should see is that really what I was just describing is you take the area of under the top function, e to the x, and then what we would want to do is subtract out the area under the blue function, which is y equals x dx, right? This is y equals x here. This is y equals x. So we did it kind of geometrically using the diagrams, but now we're going to do it properly using the mathematics. And what, by the rules of integrals, we are allowed to rewrite this as e to the minus x dx. Why is that a useful way to write it? Well, because that, again, e to the x minus x is the length of any of these vertical line segments. That's e to the x minus x. And if we add up all those vertical line segments, we would generate the area of the region. So let's continue with this. Let's do this. So the antiderivative of e to the x is that. The antiderivative of x is that. And then if we just plug in e to the 2 minus a half of 2 squared is 4, that's e squared minus 2. And then if we plug in 0, we get e to the 0 minus 0. And if we simplify, e to the 0 is 1, so we get e squared minus 2 minus 1, which is minus 3, which is what we predicted by just doing this geometrically. Of course, more often than not, the two functions, one of them is not linear, and therefore we're going to have to be able to do this mathematically, and we'll come up with the general formula in the next slide. So in this slide, we'll formalize finding the areas between two curves functions using vertical distance. This can be done also in some cases using horizontal distance, and we'll treat that later in the video. So here's a function, another function, and we would like to find the area between, let's say, A there and B here. So what would be a general formula for finding the area between those two? Well, again, we're doing this in considering vertical line segments. So for any particular value of x, there is a vertical line segment whose length we can find because we know the y-coordinate of the top function. We know the y-coordinate of the bottom function, assuming we have the equations of the functions, and that the length of that would just be yt minus yb. So as we did in the previous examples, all we need to do is to add up those vertical line segments, not physically, but actually just using integration all the way from A. So even at A, there is whatever the value of A, we could always find the length of that vertical line segment. And then there's one very, very close by, etc., all the way up to B. So if we could physically add up the length of all those line segments, we would kind of sweep out the area, the desired area. Fortunately, we don't have to calculate them by hand because the integration takes care of that. So when we integrate these vertical line segments with respect to x, remember dx, you don't actually do anything there. It's just telling you to integrate with respect to what variable, in this case, with respect to, that's mathematical shorthand for with respect to x. It's kind of saying keep x fixed for a particular value of x. This is the vertical line segment, the length of it, and the integration takes care of summing all those up, and in that way finding the area of the shaded region. So in the second practice problem, we're going to find the area enclosed by y equals e to the x, y equals negative x this time. If you recall in practice 1, we used y equals positive x. The y-axis and the line x equals 2. Now, before we dive in, it's good to just kind of sort of regroup and think about, well, we already found this area here under y equals e to the x. Remember, that was e squared minus 1. And the area under here, under this triangular region, half base times height is 2. So in this, before we were subtracting those values, this time we are going to be adding them. So I'm predicting e squared plus 1 to be the total area. But let's do this mathematically using the formula from before. So it's important to identify what's yt and what's the top function and what's the bottom function. So the top function is clearly, that must be e to the x. And the bottom function, yb, must be negative x. So then we get to just plug in, and a is 0 and b is 2. So we would have e to the x minus negative x dx. And if we simplify that, that's e to the x plus x dx. So while we're at it, this kind of shows that subtracting the functions works even when one is below the x-axis. Because think about it, with the length of this vertical line segment, this portion to the x-axis is e to the x, and then below this portion is x, and so the total length is this. So it still works. So let's use the fundamental theorem of calculus for working out definite integrals. The antiderivative of x is that, and we get to plug in, so e squared plus 2 minus e to the 0 plus 0, and that's e squared plus 2 minus e to the 0 is 1. E squared plus 1 is the total area, which we predicted by just adding e squared minus 1 plus 2, that we would get that answer. So in this practice problem, we're going to find the area of the region enclosed by these two curves or functions. So notice that you're not provided with the value of a or b yet. It looks like a is equal to 0, but not sure about what the x-coordinate of this point up here is, so we're going to have to do a little work here. Okay, so let's pull up the formula from before, and let's see what we do know. First of all, we have to establish that we don't know what a and b are yet, but we do know that yt, so y, the top function, so yt is the linear one, so this is 2x, and the bottom function is x cubed. So if we begin to put it, assemble it together, we'd have 2x minus x cubed, and with respect to x dx. And then now we have to find a and b. So to find a and b, although we have a good idea what a is, we need to find where these two functions intersect. So we must set x cubed equal to 2x. If we subtract here and then factor, we would get left with x squared minus 2 in here, which means that they intersect when x equals 0 or x equals plus or minus rad 2. Now notice we don't need the negative rad 2 because we're in the first quadrant, so we will put positive rad 2 there. And although we don't need the y value, we know that if we would just take we could just take y equals 2x. We just multiply rad 2 by 2, and we could get that the y coordinate is 2 rad 2. So now we can proceed. Let me just replace a and b here with what we know they are, which is from 0 to rad 2, and take the antiderivative, x squared minus a quarter x to the 4th from 0 to rad 2, and if we plug in, rad 2 squared is 2, minus a quarter, rad 2 to the 4th is just rad 2 squared squared, so that's just going to be 4. 0 will give 0 there throughout, and 2 minus 1 is 1, so the area of that shaded region is 1. Sometimes hard to, for students to understand how the area of such a unusually shaped region can be exactly 1, but there it is. So in some scenarios, when we're trying to find the area between two curves, we have to use horizontal distance or horizontal line segments. So let's look at an example. If we were to try and approach this using the sort of representative vertical line segment, it looks like we would just subtract the y-coordinate of the green curve from the orange curve. It looks like that would work, except when you get over here. And now that vertical line segment is not, it's really the difference between the y-coordinate of the orange curve and the lower y-coordinate of the orange curve. So this method would not be efficient to use, vertical line segments. I mean, you could work out the area up to here and then switch to another method, but that would be kind of tedious. So we have a better way, which is to consider horizontal distances. So as we did for vertical distances, if you just focus on one particular y value, you can generate that horizontal line segment, and we could find the length of that line segment. But in this scenario, we would do that by subtracting the x coordinates. So I'll call this x coordinate the one on the curve to the right, so xr, and this coordinate, x coordinate xl, and the length of that would be xr minus xl. And then, as we did before, we would sum up all those horizontal line segments. But notice now we're summing up in a vertical direction. This is all with respect to y. So we'd sum up all those horizontal line segments, but in a vertical sense. And so that's, the formula looks slightly different. So here's our horizontal line segments, and when we subtract the x, those x coordinates are going to be expressed in terms of y, as we discover shortly. Now we are going to be integrating with respect to y, integrating meaning that we're summing up those horizontal line segments, and on top of that, notice that we are changing the limits. So instead of using a and b, I'm going to use c and d because we are summing up from a low of c to a high of d. And this way we can generate the area using a different approach. So this is the horizontal method. We'll practice in the next slide. We'll practice using this on the previous example. We are going to revisit practice problem 3, which is the area enclosed by these two curves, but this time integrating with respect to y. So the formula with respect to y is given by this, and we need to establish what xr and xl are. So now we need to look at these curves. Let's see, the curve that's most to the right is y equals x cubed, and we actually have to solve that for x. So that is x equals the cube root of y, and that's our right-hand curve. On the left, we have y equals 2x. If we solve that for x, we get that. That is our left-hand curve. And so now we move over here to the formula equals the integral. We need c and d as well. Let's remember that this is 0, 0. We solved this before in the other example, and this was root 2 to root 2, if you recall. Okay, so now we are going from 0 to 2 root 2, and our x coordinates of any particular line segment. Remember, when we could have any particular line segment here. So if we want to know the length of that line segment, we do x of r. So x right, which would be, I'm going to write it as y to the third. And then x to the left is 1/2 y. And then we proceed as normal. So we take the antiderivative of this, which will be 3/4 minus 1/4 y squared. And that's from 0 to 2 rad 2. And so when we plug in 2 rad 2 to the 4/3 minus 1/4 2 rad 2 squared. Now this will take a little work, but I'm going to do, let's see, I'm going to do this one first. 1/4 2 rad 2 squared. If you multiply that out, that comes out to be 8. And then 2 rad 2 to the 4th will be 64. So I'm going to do the 4th, and I'm going to do the 4th power, leave the 3rd there for a moment, 3rd root, and then I'll come back and do that. The 3rd root of 64 is 4. And then the 4's cancel here. 4 into 8 goes twice, and the answer comes to 3 minus 2, which is 1 square unit, which is exactly what we got before using vertical line segments. So for our last practice problem, we are going to write, but we do not have to evaluate an integral expression that gives the area enclosed by these two curves. So in this one, we see once again that, well, yes, we could work with vertical line segments because one curve is above the other, but not sort of when we come over to this region. It would be a lot more complicated to work out. So what we are going to do instead is we are going to work with horizontal segments. So here's the general formula. And if I look at sort of one representative horizontal line segment, I have to come up with the x coordinates for those points. So we start with y equals x minus 1. This is clearly the linear function is the one most to the right, and then we solve for x, and we would get x sub r equals y plus 1. So for any particular y value, this would give the x coordinate of that y value on the line there. And let's repeat for this side. So this must be the curve y squared equals 2x plus 6. If we subtract 6 and divide by 2, we get that x on the left equals 1/2 y squared minus 3. So then we just get to replace equals the integral. Now c and d, well, c and d are right here, right? So see, we have to remember to take the lowest y coordinate of the region to the highest y coordinate. So we would go from -2 to 4, and x sub r to the right x coordinate is y plus 1, minus the left x coordinate for any particular y would be this. So 1/2 squared minus 3. And we have to remember that we are integrating with respect to y. So just tidy this up a bit, maybe put it in standard form because it's a quadratic, half y squared plus y, and then it would be plus 4 dy. And this is as far as we have to go because we have to write the integral expression, but we do not have to evaluate it. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.